Okay, so the first speaker will be Ms. Godot. We will have, I guess, a full talk. And you have 15 minutes and 5 minutes of questions.
Okay, I will try.
Maybe you can warn me after 10 minutes, just in case. Okay. Okay. So hello everybody. So I'm going to talk about extensions of possibility measures to Boolean algebras of conditionals, and this is a joint work with my colleagues Tommaso Flaminio and Sara Ugolini. So somehow the aim of this small work was to adapt to the possibilistic framework what is normal, what is called as Goodman-Nguyen's strong conditional event problem that was posed in the context of conditional probability. So our aim was to see how far we could go when we consider possibility measures instead of probabilities, and put it in plain words. So the question is whether we can look at possibility measures on suitable structures of conditionals, which have been called Boolean algebras of conditionals, if these plain measures can be understood as conditional possibilities. So first of all, I will quickly go through let's say main notions about conditional possibility measures that that can be found in the literature. Then I will review these structures of Boolean algebras of conditionals, and finally we will see how to relate these algebras with conditional probabilities. So so basically one can find two different approaches in when dealing with conditional possibilities. So basically the first one was how one can, so given a possibility measure on a finite, we will assume finite Boolean algebra of events, how this measure can be extended to define a conditional possibility measure. And there is a wide literature on that, starting from earlier works of Hisdall, then Dubois-Prat, Coletti and colleagues, and so on. So and basically, the proposals can be somehow can be considered as trying to solve this, we could say that this base equation, trying to solve for the variable x, which is the greatest solution for this equation. So so we want to express the possibility of A and V as a kind of product, where this product can be a continuity norm by the possibility of B. And the first proposals were actually for the particular cases when this product was taken as the minimum, and then we get this expression here, which is let's say a purely qualitative expression. Whereas there was also considered the case of taking this norm to be the algebraic product, and then what you get is this other expression, which is more in the line of conditional probabilities, I would say. But in general, one could consider this, let's say this operation star, this continuity norm, as an arbitrary continuity norm, and then get the maximal solution for that equation, which takes this form. So is the conditional possibility of A given B becomes this implication where the possibility of B implies the possibility of A and B, where this implies is modeled by the residuum of the T norm. And this let's say definition satisfies a number of rationality postulates. One could say they satisfy these nice properties that is listed here. But as you may observe here, in some of these properties there is this extra condition such that the possibility of the conditioning event should be greater than 0. This is the case of P1, but also the case of P5. And so then in a paper by Coletti, Petrucci, and Vantaggi, they propose a slight modification of this first expression, where they somehow force the value of the conditional possibility to be 0 when the conjunction of A and B is the bottom. So A and B are incompatible. So then this expression satisfies all these properties, even if the possibility of B is 0. Just a small comment here on the assumption of star being continuous. It can be observed that if we would like to somehow weaken the condition of being continuous, for instance, to be just left continuous, there is a problem because the solution for this equation might not exist. Sorry, the greatest solution for this equation might not exist, and it can be proved that that continuity of the operation star is equivalent to require the fulfillment of the base equation here, but also this generalized equation. So somehow the continuity, if we want these properties to be satisfied, we have to require continuity of the star operation. There is another approach, which is let's say axiomatic approach, where one takes the conditional possibility as a primitive notion, as it happens in the case of probability, for instance. No? And this was the proposal by Bouchon, Coletti, Marsala, where a star conditional possibility, where this star is this T norm, is a binary mapping, so mapping pairs of events from the initial Boolean algebra of events, satisfying these three properties, this CP1, CP2, and CP3. So, and these are very, let's say, reasonable properties. Notice here, for instance, that this conditional, the generalized version of Bayes' rule is one of the properties required. And this approach has the advantage that one has to care about whether the conditioning event can have or not measures 0. So it works in every case. But nevertheless, one can relate both, let's say, both approaches in the sense that the P star that was defined, here, the P star that was defined here, this TDP conditional possibility that was named in the paper, actually one can check that this is the greatest star conditional possibility in the sense of this definition that agrees with the possibility pi on A, where this pi, let's say, is just like the projection of the conditional possibility on A. So taking as conditional event the top element of the algebra. Okay, so let me just move to the brief, basic definitions of this algebraic structure of Boolean algebras of conditionals. As I mentioned, these algebraic structures arise or were proposed or studied in a recent paper by Flaminio and together with Flaminio and Hosny. And the idea there was to study this structure of conditional events in order to study their relation to conditional probability. And so here we will take the same algebraic structures, but we will try to relate them to conditional possibility. So just how these structures look like. So to construct such a Boolean algebra of conditionals, one just take the pairs. So we start from a given algebra of events, and then we consider this set of pairs of events, and then we generate the free Boolean algebra of these events. Okay, so this is let's say here everything every combination is allowed, but respecting the laws of Boolean algebra. And then in order to have, let's say, meaningful properties for these conditionals, what one does is to consider an equivalent relation or congruence relation. That means that respects the operations generated by these 5 say constraints. So these are the constraints we want to be fulfilled by our conditionals. So so you can see that these constraints are rather let's say intuitive and are satisfied by most models of conditionals. And maybe the last one, this C5, is just you can think about that as a kind of qualitative version of the chain rule for probabilities. Okay, here we require in order to be fulfilled, we require here then that A is smaller than B and B is smaller than C. Okay, and then once we have all these properties we want to have, I mean the final step is just to take a quotient. So we take this free algebra and we make the quotient by this congruence relation, and then we get let's say a Boolean algebra of conditional satisfying, let's say, all these properties. And the question here is that if you start from a finite Boolean algebra, then this algebra of conditionals is also finite. And then it's very interesting to look at what the atoms of this Boolean algebra look like in terms, for instance, of the atoms of the initial algebra. And it turns out that the atoms of this algebra of conditionals is in a 1-1 relation with sequences. These sequences alpha 1, alpha n minus 1, where these alphas are the atoms of the initial algebra. So are sequences of pairwise different atoms and of length n minus 1, if n was the number of atoms of the initial algebra. And actually the atoms take this form, take this conjunction of, you see, these basic conditionals, alpha 1 given top, alpha 1 given not alpha 1, and so on until the last member of this sequence. This is I mean, we have to know this in order to define our extensions. Just an example, if you take as the initial algebra of events a Boolean algebra with 3 atoms and thus with 8 elements, then we get these sequences of length 2. There are 6 such sequences. So the atoms of the conditional algebra will have 6 atoms, the ones this in red here. And this gives you such let's say a scaring picture of the algebra with 64 elements, because there are 6 atoms and thus 2 to 6 elements in the algebra. And here at the bottom, these are the 6 atoms, and in green, one can one can identify the initial elements of the algebra, now represented as sorry, the atoms of the initial algebra, now represented as conditionals of an atom given top. Okay, so these are the kind of structures we will deal with, and now just let's go to the 10 minutes. Okay, thank you. And so now let's see how possibility measures. Sorry, it's time already.
Yeah.
Ah, wow! I thought it was 10 minutes. Okay. Okay, so I will go quickly. So so the idea is to define. So starting from the initial algebra and a possibility measure, the problem was how to extend this measure to the conditional algebra of conditionals, such that the possibility measure here, the plain possibility measure, coincides with the conditional possibility measure A given B for a given star operation. And this can be done by first defining what is the measure on the atoms, which are given by these expressions, where here this star and the arrow are basically arbitrary T-norms and implications. So it's not necessary that one has to be the residuum of the other. And this, in fact, it can be checked as a possibility distribution. And then once you have the measure on the atoms, you can define the measure on the whole algebra by just looking at the atoms below and taking the maximum. And it happens that this way of extending the initial measure actually is a star conditional possibility, coinciding with the initial measure on the basic on the atoms of the algebra. So this somehow solves the problem that we mentioned at the beginning. So basically, basically we have shown somehow that these structures are also suitable for possibility measures, besides also conditional probabilities. And one open question is whether they are also suitable for other uncertainty measures, like, for instance, belief functions. This is far from being, let's say, trivial. And that's all. And one also can consider other classes, bigger classes of possibility measures on these bigger structures. And we would like to see how they relate to each other, to these canonical extensions. Okay, so thank you, and sorry for the extension.
Time for a very short question. Yes, there is a question.
Yes, thank you for the talk. Can you hear me?
Yes, more or less, yes.
Yes, the question is, you defined the possibility directly to the atoms, right? And then you obtained the measure for the algebra. My question is, can you directly introduce the possibility to the algebra and then recover that one for the atoms?
If you introduce, of course, you can define a possibility on the atoms of this bigger structure, and then you have the measure defined on the whole algebra. But the question was that whether this extension, when you consider the basic conditionals of the type A given B, is actually a given conditional possibility you had before. So the problem was you start with a measure in the algebra of simple events, and then the question is, can you extend this initial possibility measure on the algebra of events to a possibility measure on the algebra of conditional events, such that the measure of basic events coincides with the conditional possibility.
Yeah.
And what we have shown is that, yeah, I mean, the answer is yes, and we have shown a way to define this measure on the atom such that satisfies this requirement.
Okay, thank you. Barbara, I'm sorry, time is really over, but Louise, Barbara has a question for you, but maybe in private, because now it's time for Anouilh to speak. Thank you again, I'm very sorry, Barbara.
I cannot start sharing the screen. Now I can. No, probably. Yeah.
Okay, we see the screen.
So is it okay? Yeah. Okay, so the talk I'm going to present is a joint work with Didier and Agnès, and it's about a structure of oppositions. And in fact, I am going to emphasize a modern view, which is not much well known, I guess, and apply it to squares and cube, and even something which is a double cube, which is called also Tesseract. And it will be illustrated on different type of weighted aggregation, which are all case of Sugeno integrals. So just start with some refresher on square of opposition. So it's a very old thing, which dates back to Aristotle and to the beginning of the history of syllogism, but it gets a renewal of interest in the second half of last century. And at that time, in the last 3 decades, there has been new structure of opposition which have been introduced, especially cubes that I am going to consider in the following. And why bother on that is because it turned out that many knowledge representation frameworks, or in fact almost all, first ranging from classical logic, model logics, to things like formal concept theory, abstract argumentation, and possibility theory, and belief function, and so on, are sharing this the same structure of oppositions. And in fact, it provides tools for analyzing any of these frameworks, and possibly, for instance, to complete that and to think of operations which were not introduced initially. So just the square of opposition, the traditional square of opposition, here exemplified with a quantified statement. And you see, for instance, all A's are B's, and you have the opposite, the negation of that, which is at least one A is not a B, and which correspond to diagonals. And you have also opposition between other form of opposition, like all A's are B's, which are in opposition with all A's are not B's, and so on. And you have implication from the top vertices to the bottom vertices. Okay. And this all this logical relation in the square can be encoded logically and leads to abstract logical definition of square. So it's is a collection of 4 expressions, I would say, the logic, which for which the following logical relation holds. So, for instance, the 2 vertices A and E cannot be true together, and the bottom vertices cannot be false together. A few years ago, we introduced a gradual version of the square of opposition. Now it's no longer Boolean vertices which are true or false, which can be true or false, but for instance, they are a matter of degree, and having suitable multiple valued logic. I can extend the logical relation between the vertices, and here is an example of the graded square, where the expression corresponds to weighted minimum and weighted maximum taken about a set of evaluation xi, and the pi are just the weight of the criteria of criterion I if I view this aggregation in a multiple criteria aggregation perspective. So now the modern square. The modern square was introduced by a linguist about 10 years ago, whose name is Westerstahl, and he has identified a different square with different linguistic quantifiers, that there was an internal negation which has worked in the same time as the external negation, which is in fact the negation that we know, so the classical negation. And that there was also a duality relation between the vertices. I just explained that in a minute, in an abstract way, because in fact, Westerstahl did not provide a generic view of these modern squares, but rather many examples of them, but without abstracting the notions. And here, so I start with a binary relation, R of linking two items A and B. And so I have the classical negation between on the diagonals, as usual, as in the traditional square. But I have so-called internal negation, which corresponds, for instance, to an operation that I may apply to only one of the components of the relation, here the second item, G, but it may be the first one, or it may be both items. But the important point is that this function G or F are involutive. And if we want to call that a square of opposition, it is better that it has some flavor of opposition, which is encoded by this involutive function F or G. In fact, it is explained in the paper. You have example of traditional square which are not modern square, and vice versa. You have modern square which are not traditional square. This is due to the fact that, in fact, perhaps I should have emphasized that more on the previous slide, the fact that there is no longer any implication from the top vertices to the bottom vertices, but just a duality relation which corresponds to the composition of the internal negation with the external negation. And just an example, and this view can be extended to cube. And here you have an example with a cube where the relation is the inclusion relation, and the internal negation corresponds to taking the complement of A or B or both, and taking the negation of the inclusion relation. And then you get 8 vertices, and this cube, in fact, is both a traditional cube and a modern cube. And just view, okay, here is an example, the cube extension also of the Gradil square I showed before. And but let's go to the abstract view of the cubes. So again, my binary relation linking two items A and B, and I now have I need two functions, two involutive function F and G, that I may apply or not to the first item and second items. And I have the negation which still correspond to the diagonals, and I have a duality between top vertices and the bottom vertices. And if I can go one step further, and then I will get a tesseract, where so I need a third operation, a third internal negation, or perhaps at least a third involutive relation, because perhaps it's not exactly a negation flavor. And then I can get a second. So here the internal cube is a cube I just showed, And here now I have a third, an external cube which corresponds to the same cube, but where I have applied the H relation. This H relation may be, apart from being evolutive, maybe either a relation which apply to the first item, or to the second item, or to the relation itself. Here I choose. I made the choice of applying to the relation itself. And in fact, for an example of that, which makes sense, I will go back later on that, but we have seen, for instance, in the Gradal square, that and the Gradal cube also, that I have expressions which are based on some conjunction and implication operator. And for instance, if I have an operator which changes this pair to another pair of conjunction implication operators, I get obviously another cube. So, it is not necessarily just a formal exercise, and I will give an example of that just later. So now let's illustrate more a bit more the approach with Sugeno integral. I think all of you knows what that Sugeno integral are aggregation operators which are based on capacities, which are just increasing set function, and the so it just looks like weighted mean or weighted max expression, but before I have just a pi here, and here now the capacities apply not only to singletons but to a subset of criteria. Then, if now I want to show the modern square for Sugeno integrals, so it works very well. So I have my Sugeno integral here, taking just the complement of the degree x, which x is between 0 and 1. I have my internal negation at the bottom, for the bottom and the top, between the top vertices, and the duality which appear here is just the Sugeno integral, which are based on the conjugate capacity. So it's completely meaningful. And obviously, I have no implication from the S mu of x or S mu c of x. So it's just a pure duality, but without any implication. So it's an example of a square, which is not a traditional square, but a modern one. So I can have similar things with modern, with cube, which are, yeah, I just finished. And then, because in fact, the graded, the aggregation expression I show are also the possibility, the necessity, and the other set function in possibility theory applied to fuzzy events. And then I can organize that in a cube, which in this case is both traditional and sorry, I just miss. Okay, so I conclude out of time. Sorry. So the modern square of a richer, the modern structure, square, cube, and so on, a very rich framework for studying expression which are to which I apply involutive transformations. So, for instance, for the in the Ishkai paper some years ago, we presented a cube of opposition, but we had to constrain the capacities, separating the optimistic and the pessimistic part of the capacity for maintaining the implication relation. Now it's no longer necessary with the modern cube, since we have the duality as I show in the square. There are a few other examples of Tesseract. In fact, two other, one directly in a fuzzy version of Westerståhl, sorry, modern structures, and the other very one which corresponds to logical expression, first of this kind. And if I take the counterpart of this, the gradual counterpart of such expression, where I have a double quantification, I will get a double structure, a Tesseract for kind of double Sugeno integrals. So thank you for your attention. That's all.
Thanks a lot, Anne-Louis. As a question?
Sorry?
No, I'm looking for question in the room.
Yeah.
Yes?
The question is, you considered the modern version of the square of opposition.
Right.
My idea is, of course, you can also consider the hexagon in the same way, or not?
Yes, a good question, because yes, another advances of the last decade in structure of opposition was the introduction of the hexagon, which is indeed a very important structure. But no, for the moment, I don't know. It's a good question. It's not a natural question, but I have no modern hexagons. And in fact, the Westerstahl just consider squares and essentially squares and cubes. And later there was this Tesseract, which were introduced by a few people, but no. But I don't know about modern hexagon, but perhaps why not? But we have not succeeded to have a modern one for the moment.
You will think about.
Yeah, we should.
Other question? Hybrid questions? No? Anne-Louis, what about Choquet integrals? Does it make sense?
Yes. We have provided also some years ago traditional Q for Choquet integrals, but it has some also some constraint. And for the moment, we have not looked at the modern structure for Choquet integral. But yes, it makes sense. The only structure where the only setting which are known where we have a square but not a cube are imprecise probability. San Filippo and have provided some ECSQARU paper some years ago the square of opposition for imprecise probability, but going beyond to cube or thing like that seems to make no clear sense in imprecise probability, because we have not the counterpart of commonality, the sense of belief function. And so belief function makes cube, imprecise probability in general does not make cube, at least for the moment, because we have not the counterpart of commonality in the general case.
Thank you, Anne. Next speaker is in Prague.
Sorry. Oh, I give that. Sorry.
No.
Sorry. No. Sorry. Okay.
It works.
It should be okay.
It's okay. Thank you. Thank you.
So, Andre, you can switch off your micro.
Yeah.
Sorry. Andre, can you switch your microphone off?
Henri?
Mute.
I did it.
Thank
Yes.
you.
So hello, I'm Ismail Baj, a PhD student with the French Center for Atomic and Alternative Energy at Sorbonne University. Today I will present the paper entitled Representation of Explanation of Possibilistic Inference Decision, which is a joint work with Jean-Philippe Poli, Wassila Wardan, and Nicolas Baudet.
Just a little. Yeah.
Okay, sorry. So first I will talk about the context, which is the explainable artificial intelligence. I will remind then possibility theory and possibilistic rule-based system. I will show how we can justify the inference result of possibilistic rule-based system. From this, we will form two kinds of explanation of the possibility degree of an output attribute value U. And I will show we can represent this explanation in terms of conceptual graph. Then I will conclude with some perspective. So first, I will start with the context. So exponential generation of the decision made by AI system is now a legitimate demand. We have seen recently that a lot of laws have been adopted in order to reinforce user rights, such as GDPR in Europe. So for this, we have proposed a processing chain to generate and evaluate explanation, which take from an instantaneous AI model, we have to justify its result, which let us form an explanation that we represent. From this representation, we evaluate or we generate in natural language, this explanation. So we choose in our paper to use possibility theory, which is a well-known framework for representing imprecise or incomplete information. In possibility theory, we have two dual measures which allow us to know what is possible without being certain at all, and what is certain to some extent. Recently, Dubois and Prague unveiled the approach of Farini and Prague for the explainability of possibility theory system that I will now remind. So we consider here a set of n rule R1, R2, Rn. H rule Ri is of the form if Pi then Qi, and it is given with an uncertainty propagation matrix. So the uncertainty propagation matrix is composed of conditional possibility distribution between the conclusion and the premise, and we see that two parameters of the rule Ri and Si are between 0 and 1. So the premise is a conjunction of proposition, where each proposition is of the form Aij in Pij. Aij is an attribute applied to an item X, and Pij is a subset of the domain of the attribute Aij. Similarly, the conclusion Qi is of the form Bx in Qi, where B is an attribute applied to an item X, and Qi is a subset of dB, the domain of the attribute B. The information about the attribute Aij is represented by a possibility distribution, which is supposed to be normalized. So at least an element of its domain has a possibility degree equal to 1. In order to evaluate a proposition, we use the possibility measure with the set Pij, which let us obtain the possibility degree of a proposition and that of its negation. As consequence of the normalization of the possibility distribution of the attribute, we have that max between the possibility degree of the proposition and the possibility degree of the negation of the proposition is equal to 1. So to evaluate the premise, we extend this formula and we get the degree of the premises and that of its negation by taking the mean of the possibility degree of the proposition, and we note it alpha I, and this lets us to know to what extent Pi is possible. To get the possibility degree of the negation of the premise, we take the max of the possibility degree of the negation of the proposition, and we note it rho I, which lets us to know to what extent Pi is certain. To get the possibility degree of the conclusion and that of its negation, we perform a max-min matricial product between the uncertainty propagation and the degree of the premises and that of its negation. We note them respectively alpha I and beta I, and as the max between lambda I and rho I is equal to 1, alpha I is equal to the max between Si and lambda I, and beta I is equal to the max between Ri and rho I. To get the possibility distribution of the output attribute B associated to the rule Ri, we take the following formula, and when we have n rule, we perform a conjunctive combination of the possibility distribution associated to each rule. For our work, we take some notation. So to represent the information given by the possibility and necessity degree of a premise, we note them. We represent them by a triplet P sem D, where P is the premise, sem is either the semantic possible or certain, according to the degree D, which is either the possibility or necessity degree of P. We also introduced a formula for computing the possibility degree of an output attribute U, which is this one, where the gamma I are equal either to alpha I or beta I, and gamma I is equal to the max between a parameter of the rule, which is Ti, and it is either equal to Si or Ri, and theta I is either equal to the possibility degree of the premise as that of its negation, which is noted here lambda I and rho I. From this formula, we can set the triplet according to the gamma, which let us obtain n triplet Pi sem I di. So in order to justify the inference result, we will rely on the Farinian and Prague approach, which focused on two explanatory purposes. So how to get the possibility degree of the value U strictly greater or lower than a given tau within 0 and 1. For this, we remind that the parameter of the rule are set, and in the paper we give two necessary and sufficient conditions in terms of theta I. The other question is, what are the degrees justifying the possibility degree of U being equal to the value tau, sorry. So in order to justify the possibility degree tau, we introduce two sets that compare the parameter of the rule to the degree theta I. So we take a set GP, which takes the index where Ti is lower than theta I, and we use a set GR, which takes the index where Ti is greater than theta I. From this construction, we can take the lowest possibility degree justifiable by premises if GP is not empty, and we notice C theta. We also take the lowest possibility justifiable by the parameter of the rule if GR is not empty, and we notice CT. And from this construction, the possibility degree of tau is equal to the mean between these two possibility degrees. And from this, we can see that in some cases, we cannot justify the possibility degree tau by premises. This happens when the set GP is empty. So in that case, we see that the possibility degree of U is a mean between the parameter of the rule, and we cannot justify by premises. So in the following, we suppose that GP is not empty, and we extract the subset of premises whose degree justify the possibility degree of U, and we use the set GP, and we take the theta I, which are equal to tau, and form the corresponding triplet. From this construction, we have the following equivalence between if the set GBXU is not empty, the possibility degree of U is equal to C theta. So from this set, we will form two kinds of explanations, the justification and the unexpectedness of the possibility degree of U. So we will reduce the selected premise in order to form this explanation. And we will, for introducing this premise reduction function, use a threshold which has the following purpose. So if a possibility or necessity degree is higher than this threshold eta, it intuitively means that the information it models is violently possible or certain. So in order to reduce the premises, we will first deal with the proposition. So we introduce two proposition reduction functions. Let's take a proposition of the form AX in P, where A is an attribute given with a normalized possibility distribution on its domain. And we introduce two subsets of the domain of the attribute. The set Pi, which takes the value V in P, which have a possibility degree equal to the possibility measure of P, and another set Pn, such as the complement of Pn, takes the value V, where the 1 minus the possibility degree of V is equal to the necessity of P. From this, we can define the two proposition reduction function. P pi, which reduces P if the possibility degree of the proposition is higher than eta, and Pn, which reduces the complement of P according to the necessity degree of the proposition. It is important to notice that the possibility degree and necessity degree of the proposition are preserved. From this, we define two premise reductions which return the structure responsible for the possibility degree of computed premises and the necessity degree of these premises. And these two formula preserve the possibility and necessity degree of the premise P. We can see that from this definition, we can define also two other premise reduction functions when the possibility degree, the premises is not considered relevantly possible or certain. In that case, we return a conjunction of proposition which is not involved in the determination of the possibility degree or necessity degree of the premise. We remind that in the set GBXU, we have a set of triplets. So we introduce two other functions in order to apply the reduction function adequately according to the semantics and the premise. From this, we found two kinds of explanation. So we have the justification of the possibility degree of the value U, which is a set of possibilistic expressions that are sufficient to justify Bx is U at a possibility degree pi Bx U star U. And we introduce another kind of explanation, which is called the unexplainedness of U, a set of possible or certain possibilistic expressions, which may appear to be incompatible with this degree, while not being involved in its determination. So to understand this kind of explanation, if you consider an explainedness X, it lets us able to formulate statements such as, even if X, Bx is U at a possibility degree, pi Bx U star, sorry. It is in the same vein as the even if because statement explanation, sorry, that Darwish have introduced for binary classifier. So I will show now how we can represent this explanation in terms of conceptual graph. And for this, we will introduce a kind of conceptual graph which we name possibilistic conceptual graph. And it will allow us to represent a possibilistic expression within an explanation. So in a possibilistic conceptual graph, a concept node is labeled by a concept type, a marker, a semantic which is either possible or certain, and a degree. And this we can represent by a concept node, a proposition within a possibilistic expression of the explanation. We also extended the definition of a star basic conceptual graph. Star basic conceptual graph is a conceptual graph restricted to a relation node and its neighbor, and we extended it as a star PCG. To form from an explanation, we found an ontology which is called a vocabulary in the conceptual graph framework, and we build n+1 possibilistic conceptual graph, where n is a number of possibilistic expressions in an explanation, and a basic conceptual graph. We have a graph D which represents the observed phenomenon, the possibility degree of U. We have M possibilistic conceptual graph for representing the M extracted possibilistic expression of an explanation. And we have a root graph which let us structure the explanation by representing the link between D and the N1, N2, Nm graph. It's the link which will be represented will be either is justified by or even if, according to the explanation we want to represent. So to get the representation, we nest the graph D, N1, N2, and M in R, and we get what we call a nested conceptual graph that we define by its associated tree. And here you can see an example of representation. We use the example that is given to in the paper to represent an explanation. You can see that the phenomenon on the top is linked to the free over statement by a link which is here is justified by. And from this representation, natural language system may be able to produce explanation in natural language, such as this one. So in order to conclude, we gave a necessary and sufficient condition for justifying by real premises the possibility degree of U. We formed two explanations of the possibility degree of a value U, which is the justification and the explainedness, and we represented them by conceptual graph. And from this representation, we may be able to have a natural language explanation using energy system. So here are some reference, and thank you for your attention.
Questions? Yes,
first question. So, is there any relation of this conceptual graph in your talk to the conceptual graphs in talk of Stephen?
Exactly. Stephen used a semantic triple, which allow to represent binary relation between concepts. Mm-hmm. And we chose the conceptual graph model because it allows us to naturally represent n-ary relation when n is even if n is bigger than 2. So because in what used Stephen this morning, it doesn't allow to represent naturally NRE relation.
Thank you.
Any other questions? Okay. So thank you very much.
Thank you.
And the last speaker, are you here, Laura?
Yes.
Yes.
Hello.
Cool, hello. We see.
Hello.
Everything seems okay, I think.
Thanks. I would like to close this. Okay. Good morning. My talk concerns logic of typicality, a description logic of typicality, which is extended to the fuzzy case. And the idea is that what we start from is a concept-wise multi-preferential semantics in the two-valued case, which allows preferences with respect to concepts and has been proposed for ranked knowledge bases. And we have extended it to weighted knowledge bases in a paper in Gelia as a basis for modeling, providing models of neural networks. And what we have seen is that one can use these multi-preferential models to capture the input-output behavior of a network. And we have done this for self-organizing maps and for multi-layer perceptrons. And this allows to verify properties or by model checking over this model. But for multi-layer perceptrons, one can even see the neural network, the deep network, as a conditional knowledge base, as a weighted conditional knowledge base, provided we move to the fuzzy semantics. For multiple preference, the idea is that the relative typicality of domain individuals depends on aspects, and so that Bob may be more typical than Jim as a sport lover, but less typical as a swimmer. And there are desiderata from the multi-preferential entailment we get. And so in this paper, I studied the KLM properties of the system we obtain, of the entailment we obtain in the fuzzy case. These desiderata are satisfied in the two-valued case. And concerning the logic, the description logic we use the basic KLC, but in this talk I will focus just on the basic constructs. And so the inclusion axioms are just expressed strict properties, like all mothers of a doctor are instances of this concept, so they have at least a child who is a doctor, and concept like this. The interpretation in the two-valued case is that of interpreting a concept name as a set over the domain of domain individuals, and the relation as binary relation, a role as a binary relation. And individuals are interpreted as instances of the domain delta. So we have this, besides this kind of strict inclusions, or C's are these, we also have typicality inclusions, which have been studied in the last 15 years, and they are a way of extending to DL the description logics, the conditional assertions under different semantics have been studied in description logic, and also different closure construction have been proposed, extending the work in the propositional case. and classical logic. And here we use this different semantics based on multiple preferences. And the main idea is very simple, that a knowledge base contains a set of divisible inclusion for each concept in a certain set of distinguished concepts. And for instance, for horse, we have a set of divisible inclusion with a weight representing the plausibility of the inclusion. So for instance, the higher is the weight, the higher is the plausibility, and there are negative weights, meaning that the typicality property is not plausible. So normally horses have stripes is not plausible. Based on the weight of the feasible inclusion, one can assign a rank to domain individuals with respect to the concept horse in this case. And so in this case, Buddy gets a lower rank as it has stripes. And the way one assigns rank is just assigning a weight to each individual with respect to a concept, summing the weights of the conditionals which are satisfied by the individual. And this is a condition very similar to the criterion used by C interpretation by Kernes-Berner. So the outcome of the multi-preferential semantics can be represented as a set of spheres, a system of spheres in which a set of spheres, nested spheres, can be associated to each concept, each distinguished concept. So, for instance, the nested sphere can represent the typical domain elements with the typical horses. And the spheres for birds and for penguins may overlap, and so on. And in general, as the preference relation may not agree, one needs, in the two-valued case, one needs a way to combine them. And it has been done for the simple logic EL, which only contains intersection, not disjunction. For instance, one wants to know which are the typical employed students and whether they are young, and one needs to combine the preference for student and for employee. And in that paper, we use a modified Pareto combination, taking into account the specificity of concepts. And this is the way to evaluate the typicality. In this work, we consider fuzzy description logics in which the interpretation of a concept is just a function from the domain delta to a value in the interval 0, 1, and the interpretation of C applied to domain element X is the degree of membership of X in concept C. And here we do not commit to any combination function, to any choice of combination function. In fuzzy description logic, also axioms have a degree of truth, and we can write axiom like this. So C is included in D with the degree greater or equal to 0.6, for instance. A fuzzy interpretation in a description logic induces a preference relation over the concepts, as we can associate to each concept Ci a preference relation, a strict partial order, which is defined as follow X is preferred to Y with respect to concept Ci if the degree of membership of X in Ci is larger than the degree of membership of Y to Ci. That is, we are interpreting the degree of membership here as a typicality, a degree of typicality. And we can as well define, as in the two-valued case, the interpretation of this concept, the typical C elements, which is binary. We have defined it as binary, and it is one for those elements having essentially the maximum value of the degree of membership in C. Here we assume that interpretations are over a finite domain or they are witnessed. So we can use them. We don't have infinitely descending chains. So it's well-founded, this relation. Based on the combination function, one can define this for any concept C. So we don't need to combine further. And we can evaluate axioms, including also the typicality concept. We have studied the KN properties of this notion of typicality and of the notion of entailment, essentially. And here, so far, we have just the notion of monotonic notion of entailment. And for this notion of entailment, we want to see whether KLM property holds, and we have to map KLM properties to our new setting. We interpret this inclusion as inclusion with degree 1, and then this one as having both the two inclusions, and we interpret the typicality inclusion. Well, we have two choices, either to interpret it as A is typical, all typical A's are C with the positive degree, or as here we interpret it as A typical A are C's with the degree 1, essentially. And so we have checked which are whether these properties are satisfied in the two cases. In Zadek and Gödel logic, apart from reflexivity, which certainly cannot hold, maybe there is no domain element having a degree of membership 1 in concept C. All other postulate holds. For instance, for Lukasiewicz or product logic, or does not hold in this formulation. In this formulation, we have that all of them hold, but they fail, this formulation fails to satisfy Cauchy's monotonicity, which is actually a too strong action in this case, as formulated here. And there is a weaker alternative, which of Cauchy's monotonicity, which holds for Zadek and Gödel logic. And for the other properties, well, this version of this non-monotonic logic is weak, as in the first order, as in classical logic case, construction have been done for making it stronger, like rational closure, lexicographic closure. Here we use the construction we have seen before in the two-valued case, also in the fuzzy case. And so we just slightly modify the construction. We have to consider for all conditionals the weight of the right-hand side, which now is the weight of membership of the domain element X in the concept DIH, which in the two-valued case is either 0 or 1. And so we are back to the previous definition, but now it may be a value in the interval 0, 1. And with this kind of definition of weights, we have to, well, what we need is to put a condition to, now we have the valuation of the concepts in the fuzzy interpretation and the evaluation of weights given by these weights, these ranks. And we want these values to be coherent. And here we put this faithfulness condition, meaning that if X is preferred to Y, whether given the fuzzy interpretation of concepts, then this must be supported essentially by the weights we extract from the knowledge base. With this notion of this closure construction, we can define a notion of entailment, and this notion of entailment as well satisfies as for the monotonic case, the postulate we have seen, and fulfills most of the desiderata we had in the introduction. That is, for instance, it deals with specificity, with the relevance, that does not allow inheritance blocking. And I would like just to mention that this logic has been introduced in Gelia with the idea of modeling multi-layer perceptrons. And the idea is quite simple. That is, we build, given a neural network, here a deep neural network, we build a model over the set of the domain of input stimuli. For each stimulus, the activity of the neurons essentially defines the membership degree of that stimulus in the concept associated to the neuron. This is understandable for output for neurons in the output level, and maybe for neurons in the input level. But well, we don't know the meaning of neurons in the inner in the hidden units. However, we can, for each new unit, or for the unit we are interested in, define associate to the new unit the concept with its fuzzy evaluation, and use this fuzzy evaluation to prove formulas over these concepts. The fuzzy evaluation also induces a preference relation, and so we may see this as a fuzzy multi-preferential interpretation. And this kind of model is indeed a model of the conditional knowledge base we can extract from the multi-layer perceptron, essentially. And the time is finished. Is the time finished?
That's it. Yeah, please conclude.
Yeah, so this concludes my talk. And while the idea of associating a multi-preferential interpretation to describe the input-output behavior of the network is general and can be applied to other neural networks like self-organizing maps, the mapping of multi-layer perceptrons to knowledge bases, it's specific for this model. Thank you very much for the attention.
So please, if there are any questions? No? Or...
I have a question.
Oh, please.
Okay. Hi, Laura. You said that in the logic, in Godel logic, conscious monotonicity is not valid. And then you considered a weaker alternative version of this rule. Have you tried also other weaker version of conscious monotonicity, or just one?
Well,
There are.
Maybe there are others. Well, there is a work by Casini and Straccia, which was combining. In this work, they combined fuzzy logic with rational closure, where they actually used an encoding in which they use double negation on the right-hand side. And well, with that encoded, but they have a different semantics, substantially different semantics. They get all the postulates. So it might be that with other kind of encoding or formulation of the notion of typicality, all the postulates solved. In our case, we have not obtained this result. So it's a negative result. And it means that there is not a global preferential relation which allows us to reason on this model globally, because of the correlation of the preferential structures and KLM postulates. But well, one can reason locally, at least. This is so it's a negative result in a sense.
Oh, I don't get it really. So I was thinking if you analyze some other weaker alternative versions of.
No, I have not done this.
Okay. So thank you again, Laura.
Thank you.